What is the main motivation behind the proposed method in the paper?
The main motivation behind the proposed method in the paper is to address the deficiency in error detection, specifically targeting responses from large language models, LLMs. The paper aims to develop methods for automatically detecting errors in LLM responses by creating a benchmark, ReaLMistake, that includes objective, realistic, and diverse errors made by LLMs. The authors highlight the importance of having benchmarks with binary error annotations to evaluate error detection methods accurately. The proposed approach focuses on designing tasks that challenge LLMs to introduce errors detected by objective and diverse evaluation criteria, such as reasoning correctness, instruction following, context faithfulness, and parameterized knowledge. By creating tasks that satisfy these criteria, the authors aim to eliminate subjectivity from the error annotation process and provide a reliable testbed for evaluating error detection methods for LLM responses. The ultimate goal is to improve LLM-based error detectors by providing challenging and diverse error detection tasks that can help advance research in this area.
How does the paper address the deficiency in error detection analysis, specifically targeting LLM responses?
The paper addresses the deficiency in error detection analysis, specifically targeting LLM responses, by proposing a novel benchmark called ReaLMistake. This benchmark is designed to collect objective, realistic, and diverse errors made by LLMs. The authors identify 4 evaluation criteria: reasoning correctness, instruction following, context faithfulness, and parameterized knowledge, that cover various errors in LLM responses and can be objectively evaluated by humans. They create 3 challenging tasks: math word problem generation, fine-grained fact verification, and answerability classification, to make LLMs introduce errors detected by these criteria, eliminating subjectivity from the error annotation process. The benchmark includes error annotations on responses from GPT-4 and Llama 270B, with 14 expert annotators spending 90 hours to provide high-quality annotations. The paper analyzes the error detection performance of 12 LLMs on ReaLMistake, showing that even top LLMs struggle to detect errors made by LLMs at low recall. The findings suggest that ReaLMistake provides challenging and diverse error detection tasks, highlighting the need for further research to improve LLM-based error detectors for LLM responses.
What are the 4 evaluation criteria identified in the paper for detecting errors in LLM responses?
The 4 evaluation criteria identified in the paper for detecting errors in LLM responses are reasoning correctness, instruction following, context faithfulness, and parameterized knowledge. Reasoning correctness focuses on ensuring that the reasoning in LLM responses is logically valid. Instruction following evaluates whether the responses adhere to the requirements specified in the inputs. Context faithfulness assesses whether the responses are faithful to the context provided in the inputs without ignoring any part of it. Parameterized knowledge focuses on verifying the factual correctness of the responses without allowing LLMs to access external resources. These criteria cover diverse errors in LLM responses and can be objectively evaluated by humans, providing a comprehensive framework for benchmarking error detection methods.
Can you explain the 3 tasks proposed in the paper for making LLMs introduce errors detected by the evaluation criteria?
The paper proposes 3 tasks to make LLMs introduce errors detected by evaluation criteria: math word problem generation, MathGen, fine-grained fact verification, FGFactV, and answerability classification, ANSIELs. In MathGen, LLMs are tasked with generating math word problems that adhere to specific requirements, focusing on reasoning correctness and instruction following. The task aims to ensure that LLMs can generate questions and solutions logically and accurately, without requiring advanced mathematical concepts that could be too difficult for annotators. FGFactV involves checking if each piece of information in a claim sentence is supported by provided evidence emphasizing reasoning correctness and context faithfulness. This task requires models to provide detailed reasoning on the accuracy of each claim, ensuring objective evaluation by instructing them to check all pieces of information in the claim against the evidence. LLMs focuses on classifying the answerability of factual questions, requiring models to determine if questions contain factual errors. This task evaluates reasoning correctness and parameterized knowledge, prompting models to reason whether questions are answerable and to assess the factual correctness of the questions. Overall, these tasks are designed to challenge LLMs by introducing errors that align with specific evaluation criteria, ensuring that errors can be objectively detected by humans without subjectivity.
How many expert annotators were involved in the annotation process for the ReaLMistake benchmark?
14 expert annotators were involved in the annotation process for the ReaLMistake benchmark. The text states, 14 faculty and graduate students participate in the annotation process. Additionally, it mentions that each instance was annotated by one annotator and verified by another annotator, highlighting the thoroughness of the annotation process. The text also specifies that the annotation process took about 90 hours in total, with each case requiring 6 minutes for annotation, emphasizing the time and effort dedicated to ensuring high-quality annotations.
What are the findings regarding the performance of LLM-based error detectors on the 3 tasks in ReaLMistake?
The findings regarding the performance of LLM-based error detectors on the 3 tasks in ReaLMistake show that the error detection task is challenging even for strong LLMs like GPT-4 and Claude 3 Opus. The results indicate that the 3 tasks in ReaLMistake exhibit different levels of difficulty. Specifically, GPT-4 achieves reasonable F1 scores on the math word problem generation task MathGen, but performs poorly on fine-grained fact verification FGFactV, and answerability classification ANSIELs with very low recall. This suggests that error detection on tasks with different properties varies in difficulty, demonstrating that ReaLMistake provides error detection tasks with diverse properties. Additionally, the analysis reveals that LLMs with higher LMSYS-LO ratings, stronger models, detect errors in LLM responses with higher precision but lower recall, highlighting the challenges in LLM-based error detection. The comparison to the performance on MMLU shows consistent trends, further emphasizing the difficulty of error detection tasks in ReaLMistake.
How does the paper evaluate the error detection performance of 12 LLMs?
The paper evaluates the error detection performance of 12 LLMs by introducing a benchmark called ReaLMistake, consisting of 900 instances with error annotations by experts on responses from GPT-4 and Llama 270B across 3 tasks: math word problem generation, fine-grained fact verification, and answerability classification. The annotation process involved 14 expert annotators spending 90 hours to provide high-quality annotations. The evaluation criteria included binary error labels, error categories, and human explanations about errors. The findings of the evaluation show that top LLMs like GPT-4 and Claude 3 Opus detect errors made by LLMs at very low recall, performing much worse than humans on the error detection task in ReaLMistake. The performances of the error detectors on the 3 tasks in ReaLMistake varied, indicating diverse error detection properties. The paper also analyzed the explanations provided by LLM-based error detectors, showing that explanations were often unreliable, especially from open-source LLMs. Additionally, the paper explored the sensitivity of error detection to prompt design changes and tested popular techniques to improve LLM-based error detectors, finding that existing methods did not lead to improved error detection performance.
What are the challenges highlighted in creating challenging tasks for recent strong LLMs according to the paper?
The challenges highlighted in creating challenging tasks for recent strong LLMs according to the paper include the fact that classic objective tasks, such as mathematical reasoning at the grade school level, are too easy for recent LLMs, making it difficult to collect mistakes. Tasks that involve expert knowledge or very long context are not suitable because they are too difficult for human annotators and users of the benchmark to conduct an analysis of error detection. Additionally, while some datasets include artificially created negative cases by prompting LLMs to intentionally make mistakes, these artificial mistakes cannot evaluate error detection in realistic settings. Therefore, the paper emphasizes the importance of designing tasks that are challenging for LLMs but still feasible for humans to allow for effective error detection analysis.
What are the results of the analysis on the explanations generated by LLM-based error detectors in the paper?
The results of the analysis on the explanations generated by LLM-based error detectors in the paper show that explanations provided by the error detectors are unreliable. The study manually analyzed the explanations provided by error detectors based on GPT-4o125, Claude 3 Opus, and 3 open-source models. It was observed that GPT-4o125 and Claude 3 Opus generated relatively good quality explanations, but still made mistakes, especially on the MathGen task. On the other hand, explanations by open-source models were more often wrong, even when the binary predictions were correct. The open-source models frequently made mistakes, not just missing errors, which resulted in low precision. The analysis suggests that there is a need to make strong LLMs more cautious about mistakes in the provided responses and improve the reasoning capability of open-source models to enhance error detection performance.
How does the paper analyze the influence of prompt design on error detection performance by LLM-based error detectors?
The paper analyzes the influence of prompt design on error detection performance by LLM-based error detectors by comparing the performances of LLM-based error detectors with 4 different prompts. The analysis focuses on 2 aspects of prompt design: positional bias and wording bias. The positional bias evaluates the impact of the order of the error label options in the prompts, showing that putting the error option first results in higher recall for LLM-based error detectors. The wording bias compares 2 different wordings in error detection prompts, demonstrating that small changes in wording can affect the recall of error detection. The results indicate that recall of error detection is sensitive to these small changes in prompts. However, the study also reveals that these biases do not significantly improve error detectors, as observed by the minimal influence on the recall of strong models and the lack of consistent trends in precision for weaker models. This suggests that more complex improvements to prompts or frameworks are necessary to enhance the error detection performance of LLM-based error detectors.